Hello student, welcome in Department of Nanoscience and Nanotechnology S.Y.B.Sc class. In today's lecture, we are going to learn about the microscopic techniques, that is scanning electron microscopy, transmission electron microscopy and atomic force microscopy. So first of all, we will see the scanning electron microscopy, that is SEM. The basic principle of SEM is the SEM uses the beam of high energy electrons generated by an electron gun, processed by magnetic lenses, focus at the specimen surface and systematically scan across the surface of a specimen. Unlike the light in a light microscope, the electrons in a scanning electron microscope never form a real image of the sample. The same image is in the form of a serial data stream, that is, it is an electronic image. It is a result of the beam probe illuminating the sample one point at a time in a rectangular scanning pattern, that is raster scanning pattern, with the strength of the signal generated from each point being a reflection of differences, for example topographical or compositional, in the sample. The screen is scanned in a synchrony with the beam on the specimen in a one-to-one relationship between points on the specimen and points on the image viewing screen, that is a point-by-point translation. Increased magnification is produced by decreasing the size of the area scanned. Then working of SEM. So this is the diagram of SEM instrument. This is condenser lens, objective lens, this is electron gun, this is electron beam, vacuum pump, these are the scanning coils, these are backscattered electron detector, this is X-ray or light detector and this is secondary electron detector. So we will see the function and role of each block. First is electron gun. Electron guns can be classified into two types, thermionic gun and field emission gun. The typical thermionic electron gun consists of three parts: the filament, Venel cap and the anode. Thermoelectrons produced by the filament are accelerated through the application of a voltage between the filament and the anode, thus creating an electron beam that streams down the microscope column. The filament load current of the thermionic gun has to be set correctly. Too low a current will yield an image of inadequate brightness, whereas excessive current will reduce the working life of the filament. Some samples are especially sensitive to the electron beam and may even melt. If this happens, the electron beam should be turned down and the specimen removed from the microscope. Then electron column. The electron column focuses and illuminates the specimen using the electron beam generated by the electron gun. As the beam is scanned over the specimen in the X and Y directions, secondary and backscattered electrons are produced and detected. By amplifying and modulating the brightness of the detected electron, signals and image is produced. Magnetic lens system. The magnetic lens system consists of a condenser lens, objective lens and scanning coils. First, condenser lens. The condenser lens controls the intensity of the electron beam reaching the specimen. The objective lens brings the electron beam into focus on the specimen. The scanning coils deflect the electron beam horizontally and vertically over the specimen surface. This is also called rastering. Second, objective lens aperture. This aperture is used to reduce or exclude scattered electrons. An optimal aperture diameter should be selected for obtaining high resolution secondary electron images. Next is detectors. There are two types of detectors, that is secondary electron detector, that is SED, and backscatter electron detector, that is BSD. First one is secondary electron detector. Due to the low energies of secondary electron, that is approximately 2 to 50 electron volt, they are ejected only from near surface layers. Therefore, secondary electron imaging is ideal for recording topographical information. To attract the low energy electrons, a small bias is applied to the cage at the front end of the detector to attract the negative electrons towards the detector. A higher kilovolt is applied inside the cage, that is to the scintillator, to accelerate the electrons into the scintillator screen. Second is backscattered electron detector, that is BSD. The BSD is mounted below the objective lens pole piece and centered around the optic axis. As the specimen surface is scanned by the incident electron beam, backscattered electrons are generated, the yield of which is controlled by the topographical, physical and chemical characteristics of the sample. Both compositional or topographical backscattered electron images can be recorded depending on the window of electron energies selected for image formation. Then specimen chamber. The specimen chamber is maintained at high vacuum that minimizes scattering of the electron beam before reaching the specimen. This is important as scattering or attenuation of the electron beam will increase the probe size and reduce the resolution, especially in the secondary electron mode. A high vacuum condition also optimizes collection efficiency, especially of the secondary electrons. Specimen chamber contains specimen stage and vacuum system. So first one is specimen stage. The specimen holder is fixed to the specimen stage. The stage can be moved manually along the X, Y and Z directions. The Z adjustment is also known as the specimen height. The specimen stage can also rotate continuously. Second is vacuum system. This will vary depending on the age and type of the machine, but as an example, it consists of an oil rotary pump and an oil diffusion pump. The backing pump is used for rough evacuation while the diffusion pump achieves higher vacuums. A fail-safe circuit controls the vacuum sequence and maintains the appropriate vacuum, that is approximately 10⁻⁻⁶ torr in the optical column and specimen chamber. Pump down times will be longer if a specimen is moist. In these circumstances, it is advisable to dry the sample before introduction into the microscope. Next is operation unit. Operation unit consists monitor, text icons, image display area, active data display. The graphical user interface is displayed here. Next is text icon. This set of icons is used for switching between scan modes, starting the auto function or opening an operation window. Third one is image display area. The image is displayed here so that specimen shift and stage movement can be monitored. Data such as accelerating voltage and magnification will be visible when the image in freeze mode. Active data display. The current setting of the same is displayed here. By clicking each item, the dialog box will appear so that adjustment can be made. Last one is operational keyboard. The operational keyboard is used in conjunction with the normal keyboard and mouse. The operation keyboard controls critical operations such as focusing in high magnification and astigmatism correction. Next is applications, limitations and practical uses. First of all, we will see the applications. Scanning electron microscopy is a remarkably versatile technique. There are many different types of SEMs available to specific needs. So first application of SEM is image morphology of samples. For example, view bulk material, coatings, section material, foils, etc. Then image compositional and some bonding differences. Next is image molecular probes, that is metal and fluorescent probes. Undertake micro and nanolithography, remove material from samples, cut pieces out or remove progressive slices from samples. Then heat or cool samples while viewing them. Then next is wet and dry samples while viewing them. View frozen material. Next is generate X-rays from samples for microanalysis. Next is study optoelectronic behavior of semiconductors using cathodoluminescence. So these are the applications of SEM. Then limitations. SEM cannot take color images. The color is often added artificially in colored SEM images. Next is SEM cannot image through water. Next limitation is the SEM cannot reliably image charged molecules that are mobile in a matrix. For example, some species are volatile under the electron beam because the negative electron beam exerts a force on charged material. Next is same is not good for quantifying surface roughness at small scale. Atomic force microscope is more useful for this task. Measurement involving height cannot be taken directly in SEM. Generally, SEMs are not used for experiments involving liquids, chemical reactions and air gas systems, although some specialized machines and sample chambers do allow for these experiments. The resolution of the SEM is not high enough to image individual atoms. Elemental analysis below micron scale. So these are the limitations of SEM. Then practical uses for the SEM. Scanning electron microscopy is used in all scientific fields, in engineering, archaeology and even in art. So first practical use of SEM is forensic science, examine and compare evidence. Then material science. In this, metal, alloys, ceramics, polymers and biological material can be studied by using SEM. Then biological science. In that, large objects such as insects and animal tissues and small objects such as bacteria and viruses can be studied by SEM. Then soils and rock samples. Then medical science. In that, determine the cause of illness and develop new treatments. Then digital art, images taken from the SEM that have been modified as a digital art. So these are the applications, limitations and practical uses of SEM. Then second microscopic technique is transmission electron microscopy, that is TEM. The transmission electron microscope is a very powerful tool for material science. A high energy beam of electrons is shown through a very thin sample, and the interactions between the electrons and the atoms can be used to observe features such as the crystal structure and features in the structure like dislocations and grain boundaries. Chemical analysis can also be performed. TEM can be used to study the growth of layers, their composition and defects in the semiconductors. High resolution can be used to analyze the quality, shape, size and density of the quantum wells, wires and dots. The basic principle of TEM is the TEM operates on the same basic principle as the light microscope but uses electron instead of light, because the wavelength of electrons is much smaller than that of light. The optimal resolution attainable for TEM images is many orders of magnitude better than that from a light microscope. Thus, TEMs can reveal the finest details of internal structure, in some cases as small as individual atoms. Next is imaging. The beam of electrons from the electron gun is focused into a small thin coherent beam by the use of the condenser lens. This beam is restricted by the condenser aperture, which excludes high angle electrons. The beam then strikes the specimen and parts of it are transmitted depending upon the thickness and electron transparency of the specimen. This transmitted portion is focused by the objective lens into an image on phosphor screen or charged coupled device camera. Optional objective apertures can be used to enhance the contrast by blocking out high angle diffracted electrons. The image then passes down the column through the intermediate and projector lenses is enlarged all the way. The image strikes the phosphor screen and light is generated, allowing the user to see the image. The darker areas of the image represent those areas of the sample that fewer electrons are transmitted through, while the lighter areas of the image represent those areas of the sample that more electrons were transmitted through. Next is diffraction. Figure 2 shows a simple sketch of the path of a beam of electrons in a TEM from just above the specimen and down the column to the phosphor screen. As the electrons pass through the sample, they are scattered by the electrostatic potential set up by the constituent elements in the specimen. After passing through the specimen, they pass through the electromagnetic objective lens, which focuses all the electrons scattered from one point of the specimen into one point in the image plane. Also, shown in figure 2 is a dotted line where the electrons scattered in the same direction by the sample are collected into a single point. This is the back focal plane of the objective lens and is where the diffraction pattern is formed. The specimen preparation of tame. A tame specimen must be thin enough to transmit sufficient electrons to form an image with minimum energy loss. Therefore, specimen preparation is an important aspect of the tame analysis. For most electronic materials, a common sequence of preparation technique is ultrasonic disc cutting, dimpling, and ion milling. Dimpling is a preparation technique that produces a specimen with a thin central area and an outer rim of sufficient thickness to permit ease of handling. Ion milling is traditionally the final form of specimen preparation. In this process, charged argon ions are accelerated to the specimen surface by the application of high voltage. The ion impingement upon the specimen surface removes material as a result of momentum transfer. Next is construction of tame. So, in figure first, this is the general layout of tame, and figure second is a ray diagram for the diffraction mechanism of tame. Tame is also contain electron source, condenser lens, condenser aperture, sample, objective lens, objective aperture, selected aperture, projector lens, screen, and image pattern. So we will see the function of each part of TEM. So first of all, electron source or electron gun. The first and basic part of transmission electron microscope is the source of electron. It is usually a V-shaped filament made of a tungsten that is wreathed with Venalt electrode. Due to negative potential of the electrode, the electrons are emitted from a small area of the filament. A point source is important because it emits monochromatic electrons. In this, a positive electrical potential is applied to the anode and the filament is heated until a stream of electrons is produced. The electrons are accelerated by the positive potential down the column, and because of the negative potential of cap, all electrons are repelled toward the optic axis. A collection of electrons occurs in the space between the filament tip and cap, which is called a space charge. Those electrons at the bottom of the space charge can exit the gun area through the small hole that is less than 1 mm in the Venalt cap and then move down the column to be later used in imaging. Condenser lens. The stream of the electron from the electron gun is then focused to a small, thin, coherent beam by the use of condenser lenses. The first lens determines the spot size, the general size range of the final spot that strikes the sample. The second lens actually changes the size of the spot on the sample. Next is condenser aperture. A condenser aperture is a thin disc or strip of metal with a small circular through hole. It is used to restrict the electron beams and filter out unwanted scattered electrons before image formation. Next is sample. The beam from the condenser aperture strikes the sample and the electron-sample interaction takes place in three different ways. One is unscattered electrons, elastically scattered electrons, and inelastically scattered electrons. Next is objective lens. The main function of the objective lens is to focus the transmitted electron from the sample into an image. Objective aperture. Objective aperture enhances the contrast by blocking out high-angle diffracted electrons. Next is selected aperture. It enables the user to examine the periodic diffraction of electron by ordered arrangements of atoms in the sample. Next is projector lens. The projector lens are used to expand the beam onto the phosphor screen. Next is screen. Imaging systems in a TEM consist of a phosphor screen which may be made of fine particulate zinc sulfide for direct observation by the operator. And last is image pattern. The image strikes the phosphor screen and light is generated, allowing the users to see the image. The darker areas of the image represent those areas of the sample that fewer electrons are transmitted. The lighter areas of the image represent those areas of the sample that more electrons were transmitted. Next is application of TEM. A transmission electron microscope is ideal for a number of different fields such as life sciences, nanotechnology, medical, biological and material research, forensic analysis, metallurgy as well as industry and education. TEMs provide topographical, morphological, compositional and crystalline information. The images allow researchers to view samples on a molecular level, making it possible to analyze structure and texture. This information is useful in the study of crystals and metals but also has industrial applications. TEMs can be used in semiconductor analysis and production and the manufacturing of computer and silicon chips. Technology companies use TEMs to identify flaws, fractures and damages to micro-sized objects. This data can help fix problems and help to make a more durable, efficient product. Colleges and universities can utilize TEMs for research and studies. Although the electron microscopes require specialized training, students can assist professors and learn TEM techniques. Students will have the opportunity to observe a nano-sized world in incredible depth and detail. Next are the advantages of TEM. A transmission electron microscope is an impressive instrument with a number of advantages such as TEMs offer a most powerful magnification potentially over 1 million times or more. TEMs have a wide range of applications and can be utilized in a variety of different scientific, educational and industrial fields. TEMs provide information on element and compound structure. Images are high quality and detailed. TEMs are able to yield information of surface features, shape, size and structure. They are easy to operate with proper training. Then disadvantages. TEMs are large and very expensive. Potential artifacts from sample preparation. Operation and analysis require special training. Samples are limited to those that are electron transparent, able to tolerate the vacuum chamber and small enough to fit in the chamber. TEMs require special housing and maintenance. Images are black and white in TEM. So, these are the disadvantages of TEM. Next is difference between SEM and TEM. Types of electron observed in SEM are scattered and scanning electrons, while in TEM there are transmitted electrons. Specimen thickness of SEM is any, while in TEM the specimen thickness is typically less than 150 nanometer. Type of information obtained by SEM is 3D image of surface, while in TEM is 2D projection image of inner structure. The maximum magnification of SEM is up to approximately 1 to 2 million times, while in TEM it is more than 50 million times. Also, the high tension of SEM is approximately 1 to 30 kilovolt, while in TEM it is approximately 60 to 300 kilovolt. Optimal resolution in SEM is approximately 0.5 nanometer, while in TEM it is less than 50 picometer. Image formation in SEM is electrons are captured and counted by detectors image on PC screen, while in TEM is direct imaging on fluorescent screen or PC screen with CCD. These are the differences between SEM and TEM. Next microscopic technique is atomic force microscopy. The basic principle of AFM is used in surface sciences laboratories to obtain images with atomic resolution of 1/10 of nanometer. This type of microscopy can be effectively applied in the field of polymers to study the surface characteristics of a polymer sample. The instrument is based on the principle that when a tip integrated to the end of the spring cantilever is brought within the interatomic separation between the tip and sample, interatomic potentials are developed between the atoms of the tip and the atoms of the surface. As the tip moves across the surface, the interatomic potentials force the cantilever to bounce up and down with the changes in contours of the surface. Therefore, by measuring the deflection of the cantilever, the topographic features of the surface can be mapped out. Then working of AFM. A basic setup of AFM is shown in figure 2. The atomic force between a sample and tip are measured using laser and detector to monitor the cantilever motion. The sample holder moves the sample up and down via a piezoelectric scanning tube so as to maintain the interaction force to a pre-selected level. A three-dimensional image can finally be constructed by recording the cantilever motion in the z direction as a function of sample's x and y position. Theoretically, for any material having certain rigidity, such an instrument is always capable of producing surface images with atomic resolutions. The developments in laser technology have made it possible to detect very minute deflections of the cantilever to be detected easily. AFM can be subjected to minor modifications to suit particular applications. For example, the setup for AFM noise analysis of polymer surfaces consists of AFM head, which is fixed to a metal base. The metal base is screwed to 3-channel piezoelectric flexure stage for fine approach. The piezo stage has active feedback control with sensors for distance control. A magnetic sample holder is attached to the XYZ inertia drive for the coarse approach. This assembly is fixed to the 3-channel piezo stage. The setup is placed in a closed chamber to reduce the thermal drift. The laser diode of the AFM head is replaced by HENE laser connected to the AFM head with a single mode optical fiber. This reduces non-thermal noise which affects the stability of the laser diode. The noise power spectra are obtained with a Fourier analyzer. The spectra are one line fitted with resonance curves. The cantilever chip is glued to the half moon mount which is held to the magnets in the AFM head. AFM can be operated in 3 modes. First is contact mode, non-contact mode and tapping mode. So first one is contact mode. In this mode, the probe is dragged across the surface. During scanning, a constant bend in the cantilever is maintained. As the topography of the sample changes, the Z scanner moves the relative position of the tip or the sample to maintain a constant deflection. The motion of the Z scanner is directly proportional to the sample topography. Using this feedback mechanism, the topography of the sample is mapped during scanning by assuming that the motion of the cantilever directly corresponds to the sample topography. There are certain drawbacks associated with this mode of operation, such as there is a possibility of contamination of the surface. Damage and deformation of the samples can occur during contact mode imaging in air because significant force has to be applied to overcome the effects of surface contamination. Second drawback is combination of normal force and lateral force created by dragging motion of the probe tip across the sample and small contact areas involved result in high contact stresses that can damage either the sample or the tip or both. Second is non-contact mode. The cantilever is vibrated near its resonance frequency about 100 kHz. The tip sample separation and amplitude are the order of 1 to 10 nanometer. The tip oscillates just above the surface contamination layer. The resonance frequency and amplitude of oscillating cantilever changes as it approaches the surface due to the interactions with weak long-range forces, thus essentially imaging the surface. Either the amplitude or the resonance frequency or the amplitude is maintained constant through the feedback loop and the scanner. The motion of the scanner is used to generate the topographic image. The spring constant K is greater than the contact mode to reduce the tendency of the tip to be pulled to the surface by attractive forces. The drawbacks associated with this mode are combination of weak interactive van der Waals forces and large spring constants causes the signal to be small, which causes unstable feedback and slower scan speeds. Second is the lateral resolution is lower than the contact or tapping mode because of sample tip separation. And last is tapping mode. This mode is suitable for imaging of soft samples. Although the resolution is similar to contact mode, the applied forces are lower. The cantilever oscillates near its resonance frequency, but the oscillation amplitude is 20 to 200 nanometer, much greater than the non-contact mode. The tip makes contact with the surface for a very short duration in each oscillation cycle. The tip sample interaction alters the amplitude, resonance frequency, and phase angle of the oscillating layer. The amplitude of the cantilever is such that the probe maintains enough energy for the tip to tap, through and back out of the surface contamination layer. Next, advantages of AFM. AFM produces high-resolution images with a lateral resolution in the range of few nanometers and vertical resolution less than 1 nanometer. AFM can be used to produce images from the surface of non-conductors without any special preparation to make the sample conducting is required in SEM and TEM. Simple modification of AFM allows other properties to be detected. If the sample tip is ferromagnetic, then we can detect the stray magnetic field, thus showing the magnetic domain structure of the sample. AFM gives direct 3D images of the surface structure of polymers. By using lateral force and phase contrast modes, it is possible to differentiate the type of materials at the polymer surface. AFM is well suited for the characterization of nanocomposite materials. Radiation damage of the sample as observed in SEM and TEM is avoided. The best resolution obtained is 0.3 nanometer, which is better than SEM. Next, limitations of AFM. First, AFM is complex and susceptible to outside influences like contamination of surfaces and instrumentation control. In contact mode of AFM imaging, there is a possibility that soft polymer samples may be damaged. Next is comparison of AFM with other microscopic method. In SEM, we can determine the surface topography. In TEM, we can determine the internal morphology, lamellar and crystalline structure, while in AFM, we can determine the surface topography. In SEM, the size range of polymer structure is 10 micrometer to 0.2 nanometer, while in TEM it is 100 micrometer to 10 nanometer, and in AFM the size range of polymer structure is 10 micrometer to 0.2 nanometer. The best resolution in SEM is 4 nanometer, in TEM the best resolution is 0.2 nanometer, and in AFM the best resolution is 0.3 nanometer. The sample preparation in SEM is easy, while in TEM the sample preparation is difficult and time consuming, and in AFM the sample preparation method is easy. This is the comparison of AFM, SEM and TEM. Thank you so much.